I should have used that time when the camera was off to mention customer names. Yeah, I missed that opportunity.
You talked about big positive numbers.
Big positive numbers. Yep. Performance observability statistics are correct. Bugs happen. So there have been lots of bugs with, VMStat's pretty good, but there has been bugs. There's been lots of bugs with SAR, where if you're looking at the output and you're trying to understand an issue, it's making life harder for you because it's not even giving you correct data. So don't assume that statistics are correct. I was burnt by that with NXGE, and the byte counts were wrong. And that goes back to one of the most important skills you can learn is the art of experimentation. Applying known loads and then verifying that what you expect happened. You can actually use this to break assumptions as well. I can perform experiments to, so with client caching, if I check along the data path to confirm that my known load, if I'm moving, say, 100 megabytes a second, if I checked along each point on the switches, on the target, to see if it was moving 100 megabytes a second or 1,000 IOPS a second, that would also solve the problem. All about experimentation. In fact, if I haven't thought of a nice way to describe it, but if there's one quote that I'd like to give, that would be along the lines of, if you can't write the tool to apply the load, you can't measure the load. So if you're trying to measure lock activity, if you can't write a simple tool that exhibits a lock issue, it's very hard to measure lock activity when you don't actually understand the nature of it. Save a lot of time to sit down and write a simple C program that exhibits a lock activity, then try and learn plog_stat or lockstat. They'll make life a lot more, a lot easier for you.
Just a quick question. Have you noticed that dtrace is separating less than previous tools? It seems like it was more thoughtfully designed than some of this. Dtrace is lucky for a few reasons. It's had a very good marketing campaign. So there's been some cool tools in the past and some not so cool tools in the past. Some have slipped through the cracks. I'd name Kstats, for example, as being a great tool that, as a customer, you didn't really hear too much about, but was fantastic. Another is the SE toolkit. You could write fantastic scripts with that, but not many people knew about it. So dtrace has had a great marketing campaign, so people understand about it better. It also doesn't try and throw out a bunch of default numbers. It encourages you to program your own. So unlike VMstat, whereas here are things we decided that you should use, it gives you the capability to script. So that, in particular, has allowed it not to suffer so many of the problems. Except there was one guy who wrote a whole heap of scripts that gave to people. I guess I'm responsible for doing what dtrace was not designed for, and that is giving you a bunch of canned scripts. The reason I did that was I learned dtrace when it was beta/10 and was teaching it to customers in APAC, and they told me pretty early on, this is so difficult, I'm not going to use it. It's so difficult to learn the dtrace guide. And, well, it's not that difficult. But I was sympathetic that sometimes you just don't have, sometimes canned scripts do have a purpose. And you don't have time to sit down and read the manual yourself. You just want a starting point. You can take the canned scripts and modify them and improve them. And as inspiration, the SE toolkit, that let you code lots of useful things, but so few people ever did. Everyone used the sample scripts. Anyone use the SE toolkit, or is this story becoming too old? Yeah, one person. All right, this story's too old. If you don't know about the SE toolkit, it's kind of cool. It let you program your own observability scripts based on procfs, Kstat, and so on. These days we have dtrace, which can do a lot as well. But no, I don't think dtrace has suffered as much as other tools because the engineers didn't try and decide what's best for you. It's up to you. Things like the dtrace toolkit exist, but I've tried to make the scripts as short as possible so that you can learn and customize them. And I get lots of stories from customers who take my scripts and do other stuff with them, and that's great. So I mean, it would be great if you could actually, if VMstat was actually a script you could go and edit and say, look, I don't care about these columns, I want these other columns. I want to see major faults as well as minor faults. I don't want to see DE for deficit. I want to see more about ZFS's ARC behavior, not the page scanner. And so that's what the dtrace toolkit does. It doesn't just force you to accept one output. You can take that script and then add and remove columns as needed. In fact, it would be nice one day to replace a bunch of the statistic tools in user bin with dtrace scripts so that you could actually do that. Not so much via user bin directly, but maybe make copies and enhance them, make your own customized ones. I guess that's already happened on Mac OS X because actually, if I go to Mac OS X, so there's a whole heap of dtrace scripts in Mac OS X for observability, and they're in user bin. And I wrote most of them. But that's really great, because if you're using a tool like IOSnoop or whatever, actually Apple did a good job. They ported them, made them work well. They gave you the scripts. So you're using, like with VMstat, you use a tool. If it's buggy, you've got to file a bug. You can't do much investigation yourself. If you want to customize it, you can't. Having these things in user bin, if it's buggy, you can go read it and work on it yourself. If you want to customize it, you can. If you want to understand performance better, you can see how it's measuring things. So it's hugely useful to be able to go and read the source to the scripts you're using to analyze performance. So I was a little shocked when I heard Apple had put a whole heap of my scripts in user bin, but it is a good idea. Like I said, it would be fantastic if VMstat was a dtrace script. If a whole heap of those user bin scripts were dtrace scripts, it would be easier to understand performance. A network switch can drive all of its ports to top speed at the same time. That's another bad assumption, especially may not be true for 10 gigabit Ethernet switches. The network itself can be the bottleneck, not because of congestion, but because of the capabilities of the switches that you purchased. So don't assume that if you've got a switch with 10 gigabit ports, that they can all run at the same time. I've heard that people in the know, when they talk to vendors about it, they don't ask, I want a 10 gigabit switch with 10 ports. They say, I want a 10 gigabit switch with 10 ports that can drive all of them at the same time. And the salesperson goes, oh, okay, then you want the more expensive one. All PCIe slots are equal, or pretty much any I/O slot is equal. Tests don't assume it depends on the bus architecture, what I/O controllers they're plugged into. And I'm not just talking about the width of PCIe. I'm not just talking about by 8 slots and by 4 slots. By 8 slots can behave differently depending on the architecture. And it's not a problem with PCIe, it's just bus architecture. Don't assume that if it's that's the rated bandwidth, that the throughput can match that. Another poor assumption, adding flash memory SSDs will improve performance for everything. I might be partly responsible for this for the L2 ARC. Probably it depends on the workload. So Logzillas, there's the flash memory-based ZFS slog devices, they help synchronous write workloads. But they may not help other workloads so much. And the ReadZillas, the read-optimized second-level cache devices I worked on, particularly help random read workloads. Not so much streaming read. In fact, not at all streaming read unless you tune it. And also, why are we adding SSDs? It's assuming that hard disks are slow. They usually are, but hard disks actually have pretty good streaming performance. So hard disks can often do 100 megabytes a second streaming. SSDs, they can often do 100 to 200 megabytes a second streaming. So while flash memory SSDs can be 100 times faster than disk or 1,000 times faster than disk, in terms of throughput, they can't yet. So they may be just as fast as disks, or maybe 2 times as fast as disks. So don't assume that just throwing SSDs is always going to be a good idea. Pure streaming workloads, hard disks may be serving that just fine. Of course, maybe you want to put metadata out on the SSDs. Any other assumptions people want to share with us? Okay. Unbelievably bad performance analysis. And I've just got one example here because it is unbelievably bad. The magic 1 gigabit per second NIC. How fast can a 1 gigabit NIC run in one direction? So if it's 1 gigabit a second and it does 8 bits per byte, that's what it is, it should be 125 megabytes a second in each direction. Does that logic sound okay or suspicious? Which overhead? What overhead? Oh, okay. If you're talking about payload, sure. If you're talking about payload, you've got to think about the protocol stack and Ethernet frame check sequence values and all that stuff. I'm just talking about the bytes on the wire. It should be able to. It should be, if it does 1 gigabit, it should be able to do 125 megabytes a second in each direction. Some people have actually suggested to me that I'm not taking start and stop bits into account. That's X modem and Y modem. That's not Ethernet. Or it's a serial. No. A 1 gigabit NIC can do 125 megabytes per second in each direction. Not of payload, but just of bytes on the wire. In each direction, if it's full duplex. So in both directions, if they're both busy at the same time, a 1 gigabit NIC can do 250 megs a second. Although I can't say I've really seen that. I'm usually just doing a max workload in one direction. So 125 megabytes a second for a 1 gigabit Ethernet NIC should be the speed of light. People have sent results to me that include 120 megabytes a second. 200 megabytes a second. No. 350, 800. The record holder at the moment for 1 gigabit NIC is 1.15 gigabytes a second. It's like, wow, what NIC do you have? You should take it out and sell it. Sell it to the vendors. They should duplicate that. You've got the magic 1 gigabit NIC that's actually a 10 gigabit NIC. The problem is, I've seen this a lot where people haven't noticed the issue until far after they should have, like late in the purchasing decision, if they're doing a proof of concepts or if they're doing performance analysis, they've spent weeks on this and they haven't noticed. Another important skill for performance analysis is sanity checks. Think of ways you can double and triple check your data. Get to know your bus bandwidths, simply so that you know when something's insane. Simply so that you know that 200 megs or 350 megs a second over 1 gigabit NIC is insane, and you shouldn't be getting that. I just get this a lot. I get a lot of emails where people have made this mistake. It's usually client caching. So they've performed some test on a client, it's read from its DRAM cache, and it says, wow, I just read from that NFS share at a gigabyte a second. It's like, no, you read from your own cache at a gigabyte a second. Over the wire, it was doing much less. A couple of days ago, 2 days ago, I was sent my first 10 gigabit equivalent. Someone has measured 4.6 gigabytes a second over a 10 gigabit NIC. So they are now the record holder. A 10 gigabit NIC, it should max at 1.16 gigabytes a second. So 4.6 should not be possible. The particular scenario that made me cry the most was when it was a proof of concept with a competitor, and the customer was going to buy the competitor because their obviously insane number was higher than our obviously insane number. And it's like, both numbers are obviously insane. Please not let that be the purchasing decision. Death by complexity. This is just a reminder for me to mention performance horrors. When I was growing up and as a junior system administrator and as a system administrator, performance analysis was often considered a black art. It is hugely complicated. Eventually I figured out it wasn't that complicated. It was made complicated by not having huge amounts of documentation. There are some good books out there, like Adrian Cockcroft's book and Cyrus Internals. Tools that may not be giving you the best information, like VMstat. So eventually I realized performance wasn't that complicated, that it was tools and documentation. And since then I've been spending a lot of time working in performance and trying to help out sysadmins by giving you tools and giving you documentation so that you don't get stuck like I was when I was a sysadmin. But I have to admit, it only goes to a point. Some things are really complicated. So the TCP/IP stack, for example, is probably one of the most complicated parts of the kernel. If you're trying to understand performance of packet processing in the TCP/IP stack, it's hugely complicated. Function pointers are passed from one interface to another, so you can't just look at the code and see what function's being called. It's a pointer to a function. There's thousands and thousands of lines of code. I forget how many lines of code are in TCP/IP in total, probably 100,000. It's a huge, huge body of code. There are lots of shortcuts and code paths like snakes and ladders. So, oh, this network interface supports LSO. I'll take that code path. This network interface supports some other feature, MDT or whatever. So, I like to say performance is easy if you learn it. It's great to get into. It's not as hard as it sounds. But in a Horace talk, this is where I'll admit that sometimes it is as hard as it sounds. Sometimes it really can be awful. ZFS performance analysis. Now, ZFS is great, but it's also it's such a capable file system with so many features, and it's also been designed to have these great abstractions that you have to learn a lot of them to get your head around it. One of the nice abstractions is the ZIO pipeline. So we have a pipeline for processing I/O, and that can process I/O asynchronously. With a simple file system like UFS, when an I/O enters the stack, it just walks all the way down to the disk, and then we execute it. With ZFS, you enter a pipeline, it'll be processed asynchronously, another thread picks it up. Another thing that's complicated in terms of performance analysis. And we've been doing some of that this week in my performance class, looking at ZFS. dtrace is the savior for these, but it still takes a while to get to the bottom of them. So performance is not as hard as it sounds, but it is sometimes. There is a limit that you can make performance easy. And I think that the vendor needs to make it a lot easier for customers, but I also think customers need to learn a bit more. So there's a point where we need to meet in the middle. Often the vendor hasn't done very much. You've got some undocumented or difficult interface, and then the customer is turned off and doesn't learn so much. And so they don't get very good at performance. So we need to make it easier, and they need to learn a bit more. Bad benchmarking. Spec SFS. There is Brian Cantrell wrote a blog on this. So Spec SFS is a disk benchmark, and so we can benchmark, say, NFS. One of the problems with Spec SFS is it's been designed to be cache busting. So the presumption is when I'm testing a target file system server, I want to return data from disk. If it's returning it from cache, that's cheating. I want to see disk performance. Now, I guess that might have made sense for a very tiny amount of time until vendors said, wait a minute, cache helps performance. We're going to give you more cache. Like, that's the point. Returning from cache is the whole point of our server because we're giving you so much of it. At the moment, the Sun storage systems, you get up to 256 gigabytes of DRAM in a single head node, which is the point. The point is return from cache. So when you're applying a benchmark that deliberately busts the cache, that's not really practical. I haven't been running around enough, sorry. Thank you. I was thinking, maybe it's snow on the power lines? Okay. So one of the problems of Spec SFS is that it's cache busting. which neglects the fact that your workload may hit from the cache because we're giving you so much cache. So why be cache busting? And it also has some fairly arbitrary decisions about what the I/O types that it will apply and how many megabytes per IOP it should send. And another egregious problem with Spec SFS is it does not include price. So vendors can post Spec SFS benchmark rigs that are multi-million-dollar servers that no customer would ever buy, but it just sounds good. It's just a marketing campaign. We need to have benchmarks to help us decide what products to buy, not as a marketing vehicle that the products are just impractical. So Spec SFS could be improved if you could tune the megabytes by IOP to match the intended workload. It could also be improved if customers were to post Spec SFS, vendors were to post Spec SFS to include price performance. And so other benchmark types do that, like SBC. Copy. I've seen this a fair bit. Some people from the field tell me this is, like I've heard this described as the #1 problem with benchmarking. People are benchmarking file systems locally or over NFS by copying a file. P time, CP, this big file, to that NFS share. Your expensive server is only doing 20 megs a second, or it's only doing 100 megs a second. It's supposed to be able to do a gigabyte a second. What they've neglected to realize is when they're performing this copy, they're copying it from their local client's file system to the server. And so it's entirely bounded by local disk I/O. Copy is also a single process, single-threaded, single process. So you're not really stressing the server. Unless that was the intended work environment, was you were going to have one client run copy, it's not a particularly interesting test. So think about what the benchmark tools do. So yeah, copy. From a local file to a destination, you're testing the destination, you may test the local file by mistake, local file I/O, and vice versa. And of course, it's single-threaded, so that's a problem. Any sort of single-threaded application these days is becoming more and more and more increasingly a problem as we add more CPU cores and CPU threads to systems. So I wonder at what point will the usebin ls command become multi-threaded, because we just have so many cores. Various open source benchmark tools that don't reflect your intended workload. So the lesson is, don't run benchmark tools blindly. Learn everything you can about what they do and how close they match your environment. So have a plan. And why not write your own benchmark tool? So if you're trying to stress a server with load, if you can, write a program that simulates that client load and apply that and see how each system runs. The rule, of course, is the best way to benchmark a server is in the actual production environment. Like, see how it runs for real. The closest you can get to that, the better. But definitely just grabbing some random benchmark tool off the internet and running it, that's hit or miss. Maybe it's similar to your workload, maybe it's not at all. Misleading analysis tools. Top can also be a bit of a horror with customers. It tries to give you, some customers assume Top is giving you all the system information you need. I've actually seen a group of people who were examining performance on a system and had apparently spent weeks, and they hadn't progressed beyond Top. I don't know why. Is the impression that Top is the be-all and end-all? It tries to give you a lot of stuff, so I sympathize. Some of the problems with this is, what do these things mean anyway? What does percent CPU mean? Is that a percentage of the total CPU capacity or individual CPUs? Well, it's probably total. If it says 0.28%, is that of the last second or the last minute or the last 10 minutes? Does anyone know what CPU is? Anyone? This is Top. This is like performance tool #1. It's the same with PR stat, it's the same numbers. Gets it out of procfs. No one's game. Just pretend I'm not Brent and Gregg. Pretend I'm some random person. Like, what do you think CPU means? I'm sure you've used this.
It's all CPU.
Yeah, it's all CPUs, right? What's it?
You should target 100%. Or, I'm sorry, one core.
No, not. No. If you've got one core and you've got multiple cores, the 4 cores it should say 25%. I believe that's doing the division. But
So is it percent of total CPU operations?
percent of total CPU operations.
I guess it would be percent of.
Let me. So let me do a quick demo, just so you can see what I mean. I need a system that actually has top, which is not an easy thing. Anyone know of a system on the Swan that has top? Yeah, here we go. So this system has top. It has 16 CPUs. And I will make one core busy. How can I easily make one core busy? What's that?
Hold the spacebar down.
Hold the spacebar down? It's not fast enough.
P-bind on top.
P-bind what?
P-bind process to a specific process.
But what process do I run? Actually, I know what you mean, top. Yeah, I'm running top, so that will burn the CPU enough.
You have to find something that hogs a bunch of CPU.
Find something that... Can anyone tell me how I can make something that hog a lot of CPU? While one, do something done. Like... This is, like I've said a couple of times, experimentation is a really important thing to learn. So that's how I make one core busy. Colon is the Bourne shell operator that just does true. If I run top now, my process 9520 is burning one of those 16 CPUs flat out.
You're in contention with it.
I'm not in contention with it. I got 16 CPUs, unless other people are running stuff.
Your performance system suffered.
Yeah, my performance has suffered. Maybe that's more than one thread. It's just one thread. In fact, I may have lost networking. Nope. Something bad is happening on Steam. Okay, tops on this system. I have 2 CPUs on this system. 532, is maxed out. Only 10%? What's going on? Well, it's not showing me the average over the last second, because that is burning one core flat out. It's currently at 29%. Aggregate over a minute. If we wait for a minute, we'll be able to answer that. Anyone know the time?
You may be in contention with other processes that are stealing some of your stuff.
I may be, but you can see that it's not going to be processors. There's not much there. I don't think it's going to get to 100.
0.8% users probably your working process, mostly.
Oh yeah, there you go. That's more accurate. That's showing it to me right now. Yeah. So I've got 2 CPUs. It's going to eventually get to 50% and stop. So it is the CPU divided by the CPU count, CPU usage. When I say eventually, it's because it's not a 1-minute average or a 10-minute average or a 100-minute average. It's a exponential decay average. So there's a fancy algorithm that gives you recent CPU usage that weights more recent activity over long-term activity.
But if you kill that process, it vanishes.
If I kill it, it vanishes straight away.
So I guess recent isn't so accurate. So it's only going to get to 50%. I've got 2 CPUs. That's not on the Swan. That's on the Fishworks LAN. Cool. So there's my bash. So a lot of people don't understand what percent CPU is. Maybe part of the problem is the top man page is long, and so it's actually out of the total CPU capacity, how much that process has used recently based on an algorithm. What's misleading may also be, are they all CPU consumers? If I add up all the CPU, if I go down that column of CPU percentages and add them all up, is that all the CPU consumers? What else can consume CPU? So it may include the kernel, like, it depends on the context. It's not going to include, say, interrupt service routines. If they go and run asynchronous kernel threads, they won't be included. So a whole bunch of stuff in the kernel can consume CPU that's not in that top listing. So that's another thing misleading. You can't, if you've got a CPU problem, you can't look down this list. And often you can identify it if it's a process, but not always. Back when I used to teach performance, often I would set up a sample of this, an example of this, where I'd have a network interface consume 60% CPU and show that you just couldn't find it. Like, my CPU's busy, I don't know where it's coming from. It just wasn't visible in that output. I've asked one of my students this week on the performance class I'm teaching here to write the grand unified CPU top tool that lists out all the user land processes and kernel threads and interrupt stuff so that it does add up fully. It's possible with dtrace because dtrace can see it a lot, and he's pretty close to having it done. So it's just a big dtrace script. But finally, it's been on my to-do list for many, many years. I just haven't gotten around to it. But we'll have a script that can say, here's all your CPU consumers. This is the user land processes, the kernel threads, the interrupts, everything. Yeah, we'll get it out on there. We'll stick it on dtrace discuss, and it'll be cool.
Doesn't that like kind of say something about how the tool is used in that it seems quite obvious that you want that from the beginning if you're designing an operating system, but just take as long as you get it. Yeah, I don't know how many problems are solved by really top followed by filtering it.
Yeah. It's such a fundamental way of understanding CPU usage. And I think about this a lot. How did we end up in this situation? And part of it is the assumption that the vendor's already given you the best tools possible. And people don't stop to think, wait a minute, what do I actually want? I want to know every CPU consumer. I want to list out all the memory consumers, not just processors, but the kernel consumers all in one place. I want to look at how utilized my network interfaces are. How do you do that one, by the way? It's such an obvious question, and I don't know why people aren't thinking of it. People are. I wrote nixstat to print that out, but I think part of the problem is the assumption that the vendor's already given you the best tools possible when that's not the case. So have an open mind. Try and think about the problems you're trying to solve, and you might realize that there's some gaps. There's a whole heap of tools that we need. But yeah, it sounds obvious. Grand Unified CPU tool. Network percent utilization for the interfaces. But surprisingly, not many tools to help us. RSS resident set size. Top says res. So that could be confusing as well if it's including shared libraries that are shared between multiple processes. VMstat I would throw in here as being misleading. It's been misleading over the years, especially the free column, whether that includes the file system cache or not. Why are we telling customers about the page scanner? Depends on the system and what you're using it for, but often you get memory from the ZFS ARC to start with before you'll get desperate enough, before the kernel will get desperate enough to go to the page scanner. So it's a bit of a blast from the past. It still can be effective. If you're scanning, then things are bad.
but could definitely be revisited. Insane performance tuning. More from my performance talk of horrors. Disabling CPUs helps performance. We had this week. I was performance testing a system that had 64 CPUs, and I was doing a max IOPS workload, 4 kilobyte IOPS, and we're doing 250,000. It's pretty good, pretty reasonable. This is from cache. And poking around with dtrace, I could see that we had a lock problem. So the CPUs were flat out, but they're flat out spinning on locks. So what would happen if I disabled half the CPUs? Like just turn them off with PSR ADM? It's hard to know for sure. I got the class to vote on what they thought would happen. And so some people said it would make performance worse. Some people, I said it wouldn't make any difference. Jeff up the back said it would make things better. Turns out Jeff was right. Our performance, I turned off half of the cores on this system, and the performance went from 250,000 IOPS to 350,000 IOPS. I was playing around with, I turned off 8 more, and we got to 450,000 with only 24 cores. You turn off some more, then went down. So the sweet spot was 24 cores. Don't worry, this is not a product we're shipping to customers. If we were to ship it to customers, I'd feel a bit ashamed to have a start script that switched off all but 24 cores just to give the best performance. That's a bit embarrassing. It's an interesting experiment to do, PSR ADM to switch off CPUs, and that can help you identify scalability issues. Why does that help? If you have lock contention and you have lots of cores beating on the same lock, then only some threads can make forward progress at a time. And just having more cores beat on the same lock can increase CPU interconnect traffic, cache coherency traffic, decrease cache hit rates, and so on and so on. So fewer CPUs were better. We'll fix that lock problem before we ship that to customers. Binding network ports to fewer cores. So DLADM from Crossbow has a cool feature where it will dynamically allocate ports to cores, like you've got NGE cards or E1000G, or you can use the DLADM command to set them directly. We found that if you try to fan out the network ports on as many cores possible, performance goes down. Performance was best with 2 cores, which is like a magic number. It depends on your architecture. Try this yourself. Don't take my word for it. And some of the reasons for that would include improving the L1, L2 CPU cache hit rate, reducing cache coherency traffic, similar to disabling CPUs. Reducing CPU clock rate. I'm not sure if this would increase. In some situations, it could increase performance. If the workload is memory bound, and I see a lot these days that are, your cycles are spending so much time spinning, stalling on memory, rather than doing actual work, that you don't need those CPUs to be running at 2.6 gigahertz. Maybe you can run them at 2.1 or 1.9. And I've done a bunch of these experimentations where it makes no difference. In fact, it could help because the system runs cooler, the fans don't run as fast. Fast-running fans can cause vibration, which can cause performance issues. So, sounds insane. Less memory. I've seen a bit of this where systems with huge amounts of memory can have performance problems. Again, it sounds insane. You usually add memory is one of the most fundamental performance wins in the art. Add memory. Memory is always good. If you want to make a system go faster, add memory. The code paths have to handle it. So if you have some code path that's n squared as it's walking over memory, buffers, and it has to create linked lists to scale memory, then things can get bad rapidly when you go bigger and bigger and bigger.
Fast Fourier transform ought to be brutal.
What's that?
Fast Fourier transform ought to be brutal.
Fast Fourier transform ought to be brutal. Yep.
You know the algorithm?
The algorithm is heavyweight.
First it touches every other byte, then it touches every 4th byte, then it touches every 8th byte. Then so sooner or later it'll get 1 byte per page, which is the worst you can do.
Yep. So, yeah.
Less memory is always true to be faster if you have a JVM. So you're always going to have to hit the memory bottlenecks with the garbage collection.
And again, it's about how the code paths manage that memory. Yeah. So with the JVM, less memory would almost always be faster. Yeah, because like with garbage collect, and I'm not that familiar with the JVM, but let me just guess. If you had, say, 10 megs of memory and 100 gigabytes of memory, if you're doing garbage collect on 100 gigabytes of populated memory, it may have to scan so damn much that it gets stuck on CPU. Where if you've only got 10 megs of memory, it's pretty quick to garbage collect.
And big garbage collections are stop the world, so your application is not running currently.
Yes, big garbage collects stop the world because it's holding a bunch of locks because it's the heart of the memory subsystem. And so you're trying to work through, say, 100 gigs, and the application just stalls. And the application has higher latency. So yeah, I haven't actually run into that in Java, but it's makes sense. And you can help me run into that. That'll be cool. The two things to do is to use less memory or to work on the code paths to make them scale properly. Make garbage collect multi-threaded across the... So you run into all of these? Yep. And you're doing a lot of Java stuff?
Well, the Xeon CPUs always out on the distributed systems because their virtual threading actually hurts. So it's not the software, it's the hardware that has a problem with the switching.
Cool.
So you have to do all the odd CPUs. And then suddenly your performance jumps 3 times. That's a hardware issue that we only encountered because we had customers running on those systems and we couldn't get one ourselves. Binding network ports to pure cores on 6440s, for example, which are the sub-CMTs. If you go over 4, those are 256 CPUs in them. So you would think sending the interrupts to, 64 threads or trends would help, but actually it doesn't. It hurts the performance pretty bad. So you want to restrict to the primary core on the physical machine. So it actually boils down to write good software that scales on those systems. You need to know what the CPU architecture is, which is kind of something Java developers never want to have to deal with. We don't want to know what the hardware is. So anyway,
now
we ran into all of these, except the CPU buffer. I've never seen that happen.
Well, it may not make a difference, but maybe in a contrived way it might help. But no, those are good stories. And I like the, you've got a CPU architecture that has hardware threading. It might have 2 threads per core. And the assumption is that that's going to work, but it doesn't happen to work for your workload. And so you switch off 1 thread off every core. And so you do PSR ADM minus F, and you do all the odd-numbered cores, odd-numbered virtual CPUs. So you end up with only 1 virtual thread per core. We actually tried that this week when we were investigating our scalability problem. And we all thought that would actually be better than just turning off, say, half in a range. And we were surprised when they were both the same. So we weren't running into that particular problem. But it is very, very plausible. Warming up the KMEM caches. This one just sounds weird, but I've run into it. If you, and it's another problem with systems with massive amounts of DRAM. If you freshly boot a server, Solaris and Linux has the KMEM slab allocator. What it does is if you start accessing memory in 128K chunks or 64K chunks, it will create metadata to reference that memory. And then when you free it, it has an optimal code path to reuse those pieces of memory. So it's a cool thing. Jeff Bonwick designed it. Works really well. However, when you have a cold system that's just booted and it hasn't created all the KMEM caches to span memory, that actually takes CPU cycles. So when I'm doing benchmarks, it sounds insane. I will run a throwaway benchmark just to warm up memory, and it just warms up the KMEM caches. And then I'll delete all the data sets, unmount all the storage, and then run the real benchmark. I'm not doing it to warm up the cache hit rate. It's not about the cache hit rate. I'm throwing out the cache.
It's about having the KMM metadata structures allocated and in existence. So.
Well, that's basically measuring the system how it's going to be in use.
Yeah.
The performances aren't going to be freshly booted. They're going to be up for 120 days or 350 days.
Yes, that's a good point. I don't feel guilty about this because that's what's going to happen in the real world. You boot the system, in 10 minutes the KMM caches are warm, and then for the next 10 days they're warm. If you happen to be benchmarking a product and you boot and then immediately benchmark, it's not right. It's not quite real world. You'll get another 10% out of it if you let it warm up, if it's all cache. The curse of the unexpected is the last section. And I've got some latency things to show you that were unexpected. The two 10 gigabit ports and 41 gigabit ports, how fast can it drive Ethernet? This one burned us for a while, where I was doing 10 gig performance testing and trying to figure out why we couldn't quite scale, a lot of different system components at play. And finally, Roch Bobinet, one of the performance guys in France, said, maybe the switches are the bottleneck. We've just assumed that because they have so many ports they can drive them. Maybe they can't. I did some testing on the switches and found that the switches we had could only reach 11 gigabit bits per second total. Even though they had 60 gigabits of bandwidth in all the ports all over the switch, the thing could only do 11 gigabits. So, no, I spent a long time on the switch itself, going through all of its status tools, trying to look for pegged CPUs or some sort of bottleneck, and it just didn't explain it. One of the main things that helped me figure it out was I bought 2 more identical switches and just fanned out the workload. And then, suddenly I can go a lot faster. It's like it's the same switch. All I've done is, instead of using one switch, I'm now using 2 switches. And now it's faster. So like, of course, with fault analysis and performance testing, try to change one thing at a time. The only thing I changed was the number of switches. And I got a huge amount more performance. If there's a lesson for this one, is whenever you're doing performance analysis, try to understand the big picture. The functional diagram, as it's called, or the block diagram of every component, because any component in the data path can be the bottleneck. So think of everything: the clients, the network, the switches, that infrastructure, the server, all the hardware components, the buses, the software components. I like to draw maps of them all and write down the tools of how I measure each and tick them off. Also, that helps you understand, if you map out all the components that are at play, not only does it give you a checklist so you can measure things, some things you just can't measure. I can't measure the PCIe slot throughput directly. I haven't figured out how to do that on AMD systems. I can get to the bus that talks to the I/O controller, but I can't get information from the I/O controller. So I'm aware that that's a missing piece. But it's useful to have that awareness. So mapping out block diagrams, it lets you identify the known unknowns as well as the known knowns. Latency, heat map discoveries is the last thing for me to mention, and this is the curse of the unexpected. This is on my blog. It's called X Marks the Spot. This is from analytics. And you might not have played with analytics, but that's the dtrace/kstat based tool for the Sun storage systems at the moment. Latency is really important in the world of performance. One of the problems is in understanding latency is a lot of the tools give you average latency. We want to know more than just average latency. I want to know about the spikes. I want to know about the fast ones. So we thought about plotting it as a heat map. On the y-axis, we have latency.
So that's 0 to 9.5 milliseconds. On the x-axis is time. The number of IOs that occur at a particular latency are drawn as a dot. The number of IOs denote the darkness of the dot. So the darker it is, the more IOs fell there. Here I'm measuring NFSv3 operations per second broken down by latency. The workload, one client, one thread, doing synchronous writes, sequential synchronous writes. This sounds pretty simple. That's the latency that we got, which is really insane. There's these patterns of lines and X's. Why does latency for 1 second go down and creep up? I don't know. I have some theories. As is the case often with performance, if you don't have the tool to measure it, there can be all sorts of things that are left unnoticed. And also, if I was to guess what the latency would have been for such a simple workload, this is not what I would have guessed. So this is the curse of the unexpected. This broke a lot of heads when we first saw it because we spent a while trying to figure it out. And we believe it's because of the way allocation's happening on the disk. Since it's a synchronous write workload, NFS can only reply when it's been flushed to disk. I'm not using Logzilla devices, so this is slow. It's going all the way out to disk. And we believe that ZFS is placing data along a cylinder on the disk in such a way that as it places one block to the next, the disk has less to rotate. Just so happens that falls out of the workload that's applied and how fast the disks are spinning. I need to spend a lot more time with dtrace to be 100% sure of what's going on here. But these latency heat maps have been a real headache for us because they've shown us all sorts of things we don't understand. It's back to the unknown unknowns. All sorts of unknown unknowns we didn't know about. Now they're known unknowns, which is better than unknown unknowns, but it just creates a lot more work. So that's X marks the spot. We believe this is due to the cylinder allocation on disks and the cylinders. Here's another one that gave us a headache. This is the rainbow pterodactyl. It looks like a pterodactyl from Joust. The workload that I applied, I was performing a test where I wanted to check how fast SAS HBAs could run, how fast JBODs could run. What I do is I do a very simple streaming read from dev disk, and I light up the disks one by one until I hit some limit. So I do this sort of testing all the time, just staircase up the workload and then see what happens. So here I'm starting to hit some sort of limit, and now as I'm adding disks, the increase in performance is becoming much smaller. That scale is 1.67 gigabytes a second. The latency, this time it's disk I/O latency, has this bizarre profile. So we have, this is the beak of the pterodactyl, and then its head, the wing, and then the back. And I don't know if you played the computer game Joust. I think it looks like the Joust pterodactyl. Why does this happen? Again, we don't know. More unknown unknowns becoming known unknowns. We think that this actually coincided with 4 disks. That's where the beak turns into the head. Or is it 8? 1, 2, 3, 4. Oh, that's 8. That's right. And we think that's because this was a SAS by 8. There are 8 ports. And once we go to the 9th disk, the way it's doing its LUN allocation, it's starting to contend for that resource. So from 1 to 8 is fine. When you go to 9, we start to get contention. And so the latency becomes more erratic. Oh, that's why it changes from that one point to the next. Why is there actually 2 levels of latency? I don't know. Why does it then get better and then worse and then better and then worse? I don't know. So lots more things for us to study and learn. I've been trying to get Gregg Price to do a nice white paper write-up on this, but it's a lot of work.
How did you double check that this data is
I repeated it heaps of times. I've done it on entirely different servers, software bits, different JBODs. How did I, what's that? Yes, the same probe every time. How do I know that dtrace is probing the right thing? This is based on the disk I/O provider, and I've tested that by applying known workloads and then running IOStat versus what dtrace is telling me. So I didn't test like analytics directly here, but I have tested the provider. And like I said earlier, not to be a hypocrite, I don't trust anything I don't test. So dtrace makes it very easy for you to measure latency, disk I/O latency, and to test that it's accurate. One of the things I do is I have simple scripts. This goes back to my point about experimentation. I have simple, actually C programs or Perl programs that apply a known workload to a dev R disk so that I can then run IOStat and it has a very consistent latency. IOStat's KStat based, and then I run my dtrace script, entirely different interface, and see if the latency matches. And in fact, I did that this week in the perf class as a demonstration of the sort of thing you should do to double check this data. So please double check.